Welcome to a new test and teardown video. This time it's another HP. Model 803A VHF bridge. So this is a complete passive unit. There isn't any voltage or power supply or so in this unit. As far as I can see from the manual, the main design was done in 1955. Manual was printed in 1960, and I guess they manufactured these units all the way up to 75 or so. So I don't know exactly how old this unit is, but it could be from 55 to 75. So it is quite it is heavy. It is 28 lbs, so that is 12 a kilo. It is, as you can see, really big. So it consists of a bridge. So that means you got a generator, so an input signal and an output signal, and then the unknown. This is where you put the device you want to measure. And then it's balancing the output to become 0 if the parameters that you adjust is correct or balances everything out, right? And then you can read here how much you compensated to reach the magic 0. So if you go for magnitude, see, this is just the resistance or the impedance. So if you put on a 50 ohm resistor or a load, this is what we will call this, and you adjust this to 50 ohm. And of course it's a load that is resistive, so that means there is no angle. So if you go into 0 and you have a dip, then you know you got a load that is resistive, right? But if there is an angle, the more angle you have, positive or negative obviously, then you know it's capacitive or inductive, the unit you're testing. And of course you can measure any impedance all the way from 2 to 2 kilo. So that is amazing, the range. I'm definitely going to test how this works in real life. And what I think I want to do is I want to take a spectrum analyzer with a tracking generator and use the tracking generator here and then the spectrum analyzer input here, so I can make a curve. Normally this is not how you use this. You just set your generator to 100 megahertz, and then you just put a detector here, and then you just read the value of the level at 100 megahertz. This is exactly what it says here, 100 megahertz. However, the frequency width of this unit is very broadband. It works all the way from 5 megahertz to a gigahertz, and it's mostly accurate from, I think it was 30 megahertz and to 500 megahertz is where it's most accurate. It is explained in the manual exactly how accurate it is and how to compensate for everything at different frequencies. All right, so now I'm gonna find a spectrum analyzer and see. And we are up and running. There is definitely something wrong with this unit. There's a huge loss. I put my tracking generator at full power, removed all the attenuators, and preamp is at maximum, and then I can get a signal. And let's try and dial there. And this is a sweep from 50 megahertz to 500, and it's quite flat. And then I adjust the magnitude, see? There's clearly a dip. And see, if I go all the way up here, far away from the magic match, and I got like 650 dB of insertion loss. So there's clearly 50 dB loss. There's something that's blown here. Probably an attenuator, something probably somebody put in too much power somewhere. So, but I can still reveal something in the bridge. I mean the resistor part of the bridge. Look. Whoa. It's clearly a super dip right here. Where signal is completely gone. And look at that. 50 ohms. So I mean the resistor part works. So let's try and be at that point and now dial the phase. Ooh. And again. Let's see if we can find the magic 0 signal. And that is at 0 angle. So I mean the business end of the system here actually works. I just really need a lot more signal because it's just completely gone. That is not how it's supposed to be, right? And remember in the old days they couldn't put in a lot of power and they couldn't detect 100 dB. It's not how it's supposed to work. Whew, that was difficult. Alright, all the screws around and of course also the handle. That was okay. Look at that. Massive die cast aluminium, I guess, in one piece. And look at everything. It's just made of, I don't know, this is like how you build a tank or something. Oi, oi, oi. Look at the thickness. This is massive. I am impressed. High quality, maximum all over. Wow. And what have we got up here? So that will be a coax that goes in and out of that. I've been looking a little bit in the manual to figure out exactly what is doing what and how. Oi, 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 oi. This is good stuff. And some semi-rigid. Oh. Ooh, it's nearly touching this cable. But there's a 1/4 of a millimeter air. No, there's not even that. Cool. But it doesn't touch. Oy, 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 oy. Something is written here on this piece, and it's probably some brass. Wow, man, this is beautiful. And those are loose. Good RF shielding connection to the inside of the case. I think I'm gonna remove these so they're not gonna get lost, because I need to. Oh, this is loose as well. I need to be careful not to lose anything here, because I really want to assemble this again when I have found out exactly what is the problem. And here we go. This is the generator input. It goes straight into the resistor bridge. And ooh la la. That is a little bit sharp. Need some more air or some more light here. Let's see what we're doing. Definitely. Okay, this is good. Look at that. Fitting. That is like a high pressure hose connection. But where is the blown resistors? They will be in the resistor bridge, because here in the back there will only be timing components. So that is all this. See, all this angle stuff that goes inside them, the rear unit. They even say in the manual there's no reason to open the rear, because you can only damage the unit, but it is already damaged, and for the for the reason of science, I need to open this to document how it's made, to show you guys what is in the rear. So yeah, I'm sorry, HP, but I have to see. Wow, we are now into the rear unit. Have you ever seen a pot meter this big? It's like, I don't know, is there like 1.5 meters around here? But that is super, super cool. So that will be the 2 coax connections. And they come from each side of the bridge. See, there's another one. I don't know if that is easy. Yeah, it is possible to see that, right? So both sides of the bridge, and they go to each side of this. Is like a timing pot meter actually. So timing comes out here, and this is the detector output. The detector output comes here, goes in this coax, and here is actually a little spring joint, so this unit can move. And up here we can see the center pin goes down in the end here. So what you see here is actually a coax feed going around in there in perfect impedance all the way around. Close to that point down here is ground, of course, to follow the signal and keep the loop unique all the way around. And this is the timing. So when timing is in 0 degrees, the signals comes at the same time, and when this is in perfect center, this is 0 degrees, both time delays becomes 0 here in the middle, and then you have your signal, right? I measured down here. You can actually see the sliding point. And I measured 0 ohm to that one, to the center feed that goes to the detector output. So, I mean, we can easily close down the rear section because there's nothing here to punk around with. Everything is perfectly fine. It is not where the problem is. That's a funny sound, huh? Oh, I think it's maybe this sliding point here that needs a little bit of lubrication. I think this is Teflon. So if we try and lift this one, nope, that is not the. So it's this one that is causing the. And then you can lift this one a little bit and see. Yep. Ah, yes, of course. You got this long, sticky, pointy, and when this is grabbing like this, it can do this wee. You see? Yeah. It's not a problem. This is just how it is made. I'm not gonna put in all sorts of lubrication here because that is only causing problems. But it was really interesting to see how this is made in one solid aluminium casting, and they even milled around here to make it pretty. Can you imagine the manufacturing cost? Whoa, this would have been expensive. And this is how you tie up this. Oh, isn't it just great? And there are all the plastic pieces. They're made in tiny little pieces that you stick down here. And they probably also center align this sliding coax feed point that is connected to each of the input coaxes here. Of course, I'm not going to take anything apart here because that is just too delicate. It's definitely going to be broken if I do that. Let's look a little bit in the manual about theory of operation. See, there is a very, very good schematic explainer of how this works. So this is the generator input, and this is the test port, and this is the detector output. So if we look at the schematic, it looks like the center pin of this and that is directly connected together. And if I take my ohm meter and measure, I do get 0 ohms this way. So that is fine. Now let's look at the two couplers, the capacitive and the inductive capacitor for voltage and current. And as you see, there is a little resistor on each side. And those are of course 50 ohms to match the cables of the delay system. And those two resistors are 50 ohm, right? So that means if you look at it DC wise, they're actually connected in parallel. And if you measure on the center pin here to ground, you measure 26 ohms. So that is pretty close. So that means there's of course nothing broken. This is just the way it is. The couplings are just very weak. And also, if you look in the manual, you'll see about signal levels. Signal level is supposed to be minus 40 dB at the highest. So that is the coupling factor. This is how weak the signal is at the highest, right? And if you trim for your zero, for your actual reading, you can imagine you need to be able to measure like 80 or 100 dB below your generator. Otherwise you lose accuracy. So how did they do this back in the 50s? I don't know. So now I have assembled this nice unit again, and let's look a little bit about the insertion loss. Yes, they say 40 dB in the manual. I don't exactly see that I can do that. See now, my tracking generator here is connected directly to my RF input, and look at that, 0 dB. Okay, and my tracking generator is at maximum, and now I open this and I got minus 70, right? So let's try and connect the tracking generator to the generator inputs. See, that is the kind of signal there is. There is absolutely nothing, and I don't have anything here. Okay, so that is, so it's not 40 dB, definitely not, right? It's, I don't understand how this is possible, because the resistors measures correctly, everything measures correctly, so how the heck is this possible to have this problem? Obviously I can go in and in my amplitude I can remove the attenuator. So now I put my ref level all the way up. So this is my noise floor in the spectrum analyzer, including full preamp and full attenuation is off, of course off. So now I'll be able to measure something, right? But it's, I am that many dB from noise floor, right? And that is with modern equipment. So how the heck could they do this in 1955? And let's put on the 50 ohm resistor, dial the, ooh, see here is a magic reference resonance, and now I can poke with the phase. Well, that's funny. And then it falls. Whoa. And that is my 0. And it just hammers to my noise floor. So maybe you need a preamp or a super crazy sensitive something. Ooh, there's a little bit. Or maybe a power amp here to put in some more. Oh my gosh. But I think this concludes this video of this fantastic VHF bridge. Thank you very much for watching.